Welcome to this lesson on inductive reasoning. Make sure you have a math dictionary handy as you will be adding more words to it. The first being inductive reasoning. If you want to pause the video now to copy this down, do so. Conjecture, an unproven statement that is based on a pattern or observation. I've observed that every year Art Dave grows a beard. So this year, my conjecture would be Art Dave is going to grow a beard. Counterexample is an example in which a conjecture is not true. So if you can prove it, false. If my conjecture was all animals have black fur, is this a true statement? I would say no, it's false, because I can think of a golden retriever has a blonde or a gold fur. You can think of any other conjecture or any other example that makes this false by just thinking of an animal that does not have black fur. When we use our inductive reasoning skills, we look at making predictions, and it's all based on your observations. So if we observe this pattern, the next shape, if we want to see what would the next shape be, I would draw this. Okay, I know I did a bad. I'm not very good at making perfect squares, but there's 5 on the bottom. Then I can see it goes to 4, then 3, then 2, then 1. Something like that would be my prediction of the next shape. Some people see it growing a little bit differently, and maybe I see it extending 1. So maybe you see that there's a whole new row going on. But at any rate, you're looking for pattern observation. That's inductive reasoning skills. Looking at a pattern and trying to come up with solutions. So for example, this pattern, if you were asked what would the next shape be, well, I would copy this last shape, and what I see is an extra this little shape would be added on. That would be the next one. Let's take a look at this in numbers. It says find a pattern for each sequence. Use the pattern to show the next two terms. So if I'm looking at this, we got 1, 3, 9, 27, 81. Well, it doesn't go up by the same increment because it goes up by 2, then 6, then it jumps all over the place. So it's not adding something. What about multiplying? If I do 1 times 3, I get 3. 3 times 3 is 9. 9 times 3, 27. I think we found our pattern. 27 times 3, 81. So the next term would be 81 times 3, which would be 243. Then we'd have to take 243, multiply that by 3, in which we would get, let's see, 243 times 3, 729. There's my next two terms. Sometimes we'll have an example where we need to show that a conjecture is false by finding a counterexample. Any example that proves that it's not a true statement. So if I look at number 3, it says if the product of two numbers is even, the numbers must be even. So it's saying that if the product of two numbers, so let's say 2 times 2, if the product, the end number, is even, then the numbers we started with have to be even. Here's my counterexample. Based off 2 times 2, I know that if I did 2 times 3, I get 6, where my product is even, but both the numbers that we use are not. 2 is even, but 3 is odd. Therefore, this would be my counterexample for number 3. Let's look at my answer for number 4. If a shape has 2 sides the same length, it must be a rectangle. So 2 sides have to be the same length. Then it must be a rectangle. Well, I can think of 2 examples. I can think of a square because it has at least 2 sides. If we want to get more specific, I think of an isosceles triangle where those 2 sides are the same. So this shape right here has 2 sides that are the same length, and it is not a rectangle, it's a triangle. Let's look at one more conjecture proving it's false. All plurals end with the letter S. We need to find a counterexample. Think about.
Are you talking to me?
CJ just interrupted the video. All plurals end with the letter S. All you have to do is think of a plural word that does not end in the letter S. Here's my word. CJ.